Hi guys, so we are going to talk about section 2.2, which is graphs of polynomial functions. You explored a little bit in class today, but we're going to take it a little bit further now with our notes. So there are two basic features of the graphs of polynomial functions, one being that they are continuous with no breaks, and the other is that they have smooth, rounded curves. So some examples. Here we have couple of different graphs here, and what I want you to tell me is, are they graphs of polynomial functions? So take a second to browse through them, take a look at, are they continuous? Are there breaks? Can you draw it without picking your pencil up? Hopefully you're able to see that, one second, let me grab a pen. Hopefully you're able to see that yes, this is a polynomial function. Yes, this one is a polynomial function. This one would be a no because we have this break here where we'd have to pick up our pencil. And for this one here, we have a sharp turn, so it's not smooth, rounded, so this one would also be a no. All right, so thinking about the graph of x to the 7th, will it look more like x squared or x to the 3rd? And we actually talked about this already a little bit in class. It will actually look more like a cubic graph because the degree is odd. So what makes them look the same is that the fact that it's odd. So odd or even graphs will always look the same. We also have polynomial functions in the form of x to the nth. So something like this where you're raising it to a power. They're actually called power functions, just so you know that. All right, now so let's think about these graphs and what they would look like. So this graph is negative x to the 5th. So since it has an odd degree, that means that it is going to look similar to an x cubed. Just come out similar to x cubed. But since the leading coefficient is negative, we know that it is actually going to be decreasing. So it will look something similar to starting up and decreasing down. Sorry, my drawing is not that great right now. For B here, this is going to be something that is similar to an x squared because it's even. So it's an even degree, and it's going to be similar to an x squared. Since my leading coefficient is positive, and I think about an x squared is going to just have a parabola opening up. Since it's positive, same thing is going to happen here. What we talked about in class today about finding x-intercepts and determining whether or not it's going to go through or be tangent, we're going to kind of pull that in later. So for right now, I will just briefly touch on that. Sorry, I can't draw a straight line here. If you have a coordinate plane here and we want x plus 1 to the 4th power, that means when x is at negative 1 right here, since it's raised to an even power we said is going to be tangent, so it is going to be something along the lines of this. Ignore this line right here. Sorry about that. All right, so let's talk a little bit more about that leading coefficient. So definition of the leading coefficient test basically says as x moves without bound to the left or the right. So the way you saw it written earlier today in your packet was as x approaches negative infinity or as x approaches positive infinity. I want you to tell me what the graph is doing. Is it rising or is it falling in the sense of your y values? So if n is even and the leading coefficient is positive, so even, an example of an even would be like x squared. If n is even and the leading coefficient is positive, then that means it's going to rise to the left and also rise to the right. If it's an even degree and your leading coefficient is negative, as in a negative x squared, it's going to fall to the left and fall to the right. If it's odd, something like an x cubed, x cubed, we know we have it going in each direction, it's going to fall in one direction and rise in the other. So if A is positive, then it's going to fall to the left, rise to the right. And if A is negative, it's going to rise to the left, fall to the right. So when I'm asking you to explain or tell me what you know from the leading coefficient test on an assessment of any sort, you can just actually even draw these arrows. Don't even need to explain any further in words. This tells me that you know what's going to actually happen with this graph. So try a couple of these. Describe the right hand and left hand behavior. So that's basically what we're looking at. We're looking at the end behavior of our graphs. So I will do this first one with you. If it is a negative and it's an odd degree, negative leading coefficient, odd degree. So an odd degree says you're going to have one in each direction, but since it's negative, it's going to rise to the left, fall to the right. Next, we have a positive leading coefficient and an even degree. So positive says it's going to rise to the right and the left. Okay. For C here, we have a positive and an odd. So therefore, it's falling to the left, rising to the right. It's increasing as we move across our X. All right. Next, let's talk about zeros of polynomial functions. And this basically is something that you hopefully already know. It's just finding the values of X and that describe your turning points. So on the graph of a polynomial function, turning points are points at which the graph changes from increasing to decreasing or vice versa. So these are considered our relative maximum or minima, which we already talked about in a previous section. Let f be the polynomial function of degree n. The graph of f has at most n minus 1 turning points. So the function f has at most n real zeros. So for example, if you have a degree of 4, it will have 3 turning points, and it will have at most 3 turning points and at most 4 zeros. There's an example for you. It doesn't necessarily mean it's going to have 3 or going to have 4 of those. However, it will have at most. So if you come up with anything more than 3 turning points or anything more than 4 zeros, then you did something incorrect along the way. All right, so let f be a polynomial function and let a be a real number. List 4 equivalent statements about the real zeros of f. So these are all standard statements about the real zeros of any given function. So x equals a is a 0 of the function, then x equals a is a solution of the polynomial equation as well. X minus a is a factor of the polynomial, which is what we've been looking at. This is what we saw on your packet today. And then also a comma 0 is an x-intercept. Again, this is what we saw on your packet earlier today. So if we take a look at this example, and we want to find all the real zeros. So you can start by factoring out a GCF here. So you can take out a negative 2x squared. And when you take out a negative 2x squared, you're left with x squared minus 1. So then we have negative 2x squared, and then this is a difference of 2 squares, so x plus 1, x minus 1. So this is our completely factored function. Going back up to our original, it has a degree of 4, so therefore it can have at most 3 turning points, and it can have at most 4 zeros. Taking a look at our answer here, when we take each factor and set it equal to 0, this first factor set equal to 0 is just going to be the intercept 0, 0. Our next one is going to be, negative 1, 0. And our last one is going to be a positive 1, 0. So we have 3 turning points here and 3 zeros. This particular problem, because of this x squared, we have that double 0, 0 as an ordered pair. Okay? Okay, now we're going to talk about repeated zeros, which is what we actually just saw in that previous example. Sorry, I was locating my pen there. So a factor of x minus a to the k, where k is greater than 1, yields what is called a repeated zero, where x equals a of multiplicity k. So you're going to start to hear this phrase multiplicity a lot. So if k is odd, then that means it's going to cross the x-axis. So it's going to go through. The words we used today were through and tangent. If k is even, then it's going to touch or be tangent to the x-axis. So in this quick example down here, if you have a polynomial where the x equals 3 has a multiplicity of 4, then that means it's going to touch the x-axis at x equals 3. If you have a 0, x equals 4 with multiplicity of 3, since it's odd, it's going to go through. Sorry. Okay? Pretty easy, since you already explored that earlier. All right, last page here. We have, if you're trying to sketch this function, 3x to the 4th minus 4x to the 3rd, the leading coefficient test tells us that it has an even degree, positive leading coefficient. So that means it's going to rise to the left and rise to the right. It's going to rise in both directions. So if you're trying to find your zeros here, let's take out a greatest common factor of 3x to the 3rd, and then we have x minus, whoops, not 3. I'm sorry, hold on. Backtrack. Let me erase that. Try that again. You're only taking out, in this problem, a x to the 3rd. Sorry. So you have x to the 3rd, and then you have a 3x minus 4. So here's your factor and answer. Your solution, or your zeros, would be x equals 0 and x equals 4/3. So what we want to do now is test our intervals to figure out what our graph is really going to look like. We know that it has to have at most 3 turning points and at most 4 zeros. So it actually only ends up having 2 zeros because we do have 1 0 with a multiplicity. So the test intervals, what you want to do is you want to think of intervals that relate to your zeros here. So the intervals I'm going to test are negative infinity to 0, and then I'm going to test 0 to 4/3, and then 4/3 to positive infinity. And I want to pick a value that is somewhere within those intervals. So I'm going to choose -1, 1, and 1.5, just because they are pretty easy to work with. So when I plug them in, and you can do your calculations on your own, but I'm going to get the following calculations, or the following results. Being that the signs are positive, negative, and then positive again, points that are on the graph, I'm going to take these two and put them together. So you have -1, 7, and 1, -1, and then 1.5 and 1.6875. So these are your ordered pairs. You can take these 3 ordered pairs, plot those along with your zeros, and along with knowing what your graph is going to look like as far as its end behavior, you should be able to graph this function pretty accurately without your calculator. Okay? And I'm not going to do that graph for you. All right, last thing we have here is, something called the intermediate value theorem. We'll discuss this a little bit further in class and give some more examples, but for now, what I would just suggest you doing is copying down this definition. For the intermediate value theorem says that if you have a point, if you have, 2 points on a graph such that the y values, the solutions of your function when plugging in a and b are not equal, then for any number, let's call it d, between those 2 y values, there must be a value c that is not equal to a or b as well. Kind of confusing. To describe how the intermediate value theorem test can help in locating the real zeros, what we want to do here is if you can find a value, x equals a,